My name is Reuven Shavit, and I will be talking about the dipole antenna. The term of dipole antenna was first introduced by Marconi back in 1895 while he was experimenting radio wave communication experiments, and this term was adopted by the scientific community since then. We cannot talk about antenna without paying some tribute to few giants, scientific giants from the 19th century, which actually laid the foundation for the theory of electromagnetism. And the most notable are James Maxwell, who was the first to formulate in 1865 the mechanism and principles of electromagnetic propagation by four simple vector differential equations, and Heinrich Hertz, who in 1886 was the first to demonstrate experimentally their validity. Today, we understand that electromagnetic radiation is caused by an accelerating electrical charge. The two vector quantities which characterize the electromagnetic radiation are the electric field, E, with parameters x, y, z, and t, the time, and the magnetic field, H, with the same variables. The interrelation between these quantities can be described by Maxwell four differential equation, which we can see them here. Rotor E equal to the derivative of the magnetic induction, which is also called Faraday law. Rotor H, which is the derivative of the displacement field, plus J, the electric current, which is also called the Ampere law. Divergence D equal to rho, which is the electric charge, which is also called the Gauss law for the displacement field, and divergence B equal to 0, which is also called the Gauss law for the magnetic induction. Those four equations are not enough to solve the numerous variables in those equations. And therefore we need some extra equation in order to have a unique solution of the problem. And the extra equation are the continuity equation, divergence G equal to the derivative of the electric charge, and the three constitutive relation which relate actually the displacement field to the electric field through epsilon, which is the permittivity. The magnetic induction, B, is related to the magnetic field H through mu, which is the permeability, and the induced current J is related to the electric field by sigma, which is the conductivity. So what is an antenna? In principle, an antenna is an energy converter which transforms electrical currents into electromagnetic fields, and vice versa. It is doing that in a similar fashion to what a speaker is doing to acoustic waves or the ear to the acoustic waves. The simplest type of antenna is the dipole. It's made of two conductive arms, connected at its center to a voltage generator. And the variation of the electric currents generates the electromagnetic radiation. What we can see here actually is the dipole connected to the voltage generator, and the variation of the signal actually radiates electric fields which are plotted on this sketch. And the signal being a periodic signal, we have here the electric field lines at three instances, T over 4, T over 2, and T, where T is the periodicity in time of the signal. What we can actually note that for the traveling charges along the dipole, actually they induce electric field, and this electric field actually separates from the dipole and start to propagate on their own a phenomena which is very similar to what happens when somebody is smoking and is releasing smoke rings in the space. For an elementary dipole with infinitesimally length and current delta t, which is Dirac delta, Maxwell equations can be solved analytically, and the radiated field in time domain are described by those two expressions, in which delta t is the Dirac delta, delta dot is the derivative of the delta function, ut is the unit step function, and c is the speed of light. Now a few words about those equations. What we can note, first of all, that all the functions involved here, their variables is t minus r over c. T is the time, and r over c is the time delay, which takes to the signal to travel from the origin to the observation point. Second observation is that the electric field has two components. One is radial, and the other is transverse in theta direction. Now, in terms of amplitude dependence, we can note actually that the electric field actually is dependent on r, or in r to the square, r square, and r to the third power. For very small distances, the dominant term is r to the third power, while for large distances, the dominant term is 1 over r. The same can be said about the magnetic field, in which the dependence on amplitude is 1 over r and 1 over r square. In terms of the angular dependence of the electric field, we can note actually that at large distances, since this is going to be the dominant term, the electric field dependence on theta is sine theta. Therefore, in the zenith and in the south pole, actually, we don't have any radiation, neither magnetic or electric, since theta is equal to 0 or theta equal to pi. For large distances, the electric field as well as the magnetic field are proportional to the derivative of delta, which is the current distribution. This is a very important conclusion. A very important observation actually, that the electric field and the magnetic field are proportional to the derivative of the current distribution on the antenna. Next we'll talk about harmonic time dependence of the signal, which is a particular time of the time dependence, but a very common and a very important one. The electric field can be, in this case, described by E equal to a phasor or a complex amplitude, E, x, y, z, multiplied by the exponential to the j omega t, in which this is the time dependence, and in which omega is equal to 2 pi f is the angular frequency, f is the frequency, and as I mentioned, EXYZ is the complex amplitude of the field. Two additional parameters which characterize the electromagnetic radiation are the wavelengths, lambda, which is actually the distance for which the electric field repeats itself, and the phase velocity, Vp, which describe actually the propagation of the phase of the electric field. These quantities are interrelated through the expression or the identity Vp equal to the product of the wavelengths multiplied by frequency. In the special case of an elementary dipole with infinitesimally lengths, the radiating fields are described by those equations. Actually, those equations are derived from the previous two equations when we substitute this expression of the electric field into the previous equation, and we get here the performance of the electric field without the time dependence. In terms of amplitude dependence, we have the same kind of dependence as previously, 1 over r squared, and 1 over r to the third power. The E minus jkr actually here represents the phase delay between the phase of the electric field relative, at the origin compared to the phase of the electric field at the observation point. K is here the propagation constant and is equal to 2 pi over the wavelength or equal to omega multiplied by square root mu epsilon. What it's interesting to note here is that for large distances, as I will mention later on also, we obtain actually one term for the electric field, which is actually this term. And for the magnetic field, we get one phi, which is an azimuth vector, and those two are orthogonal vectorially. Now let's consider what happens with the radiation from the dipole when we consider three distant ranges. The near field, at which the distance of the observation point is less than lambda over 2 pi. The intermediate range, which is also called Fresnel zone, at which r is smaller than Td squared over lambda, with d being the diameter of a sphere encircling the antenna, and lambda is the wavelength, and r is bigger than lambda over 2 pi. And there is the far field, or the Fraunhofer zone, at which is determined by the upper bound between those two quantities, r larger than 2d squared over lambda or 5 lambda. What happens that for very large wavelengths, the dominant term is 5 lambda, while for very small wavelengths, the dominant term is 2d squared over lambda. In the near field, the electromagnetic fields of the elementary dipole can be approximated by this expression in terms of the magnetic field is 1 over r squared sine theta, and the electric field is 1 over r to the third power and has those two components. What is interesting to note here that if we also compare those two expressions to the electric field of just a simple dipole made up of two opposite charges, q, separated by a distance d on the z-axis, we obtain the same type of expression as the expression we obtain for the elementary dipole for the electrodynamic case. Therefore, we can actually conclude that the near field of the dipole antenna, and also we can extend this concept also to other antenna, is very much related to the quasi-static electric field of the problem. And this helps in many cases to understand the physics of the behavior of the electromagnetic fields in the near field of the antenna. Now let's go to the far field of the electromagnetic fields of the elementary dipole. In this case, the electric and magnetic fields can be approximated by those two expressions, H and E. What's interesting to note that the amplitude dependence is 1 over r with the phase delay e to the minus jkr, and actually e to the minus jkr over 4 pi r represent actually a spherical wave propagating from the source. Sine theta, in this case, represents the angular dependence of both electric and magnetic fields on theta. Another interesting observation is that the electric and magnetic fields are orthogonal in terms of vectorially, since 1 theta and 1 phi are orthogonal in space. And the ratio between E and H is called also the characteristic impedance, denoted by eta equal to square root of mu over epsilon of the medium. This impedance is equal to 377 ohms in free space. The orthogonality between the magnetic and electric field for far field approximation can be actually represented by this equation. H is equal to 1r, which is the propagation of the spherical wave, multiplied vectorially by the electric field and divided by the characteristic impedance. Conceptually, the radiative far field for a finite length L dipole, which is an extension actually of the elementary dipole with with arbitrary current distribution IZ prime, can be considered as a superposition of the fields from all the elementary dipoles which make the entire current distribution here. We can actually get the total electric field by integrating this electric field over all the dipoles, elementary dipole, which make up the entire finite length dipole. And this can be expressed by this integral. What's interesting to note here is actually, if we denote k cosine theta by u, we get here in the integral, under the integral, a Fourier transform. Therefore, the electric field actually for far field approximation is proportional to the Fourier transform of the current distribution. And all that, of course, is multiplied by sine theta, which is actually representing the radiation pattern or the angular dependence of an elementary dipole, and e to the minus jk r over 4 pi r, which actually represents the spherical nature of the dipole in far field. J omega here in frequency domain actually is translated into the time domain to derivative with time. And this is actually, we can actually see the same conclusion that we derived previously. Now let's consider few current distribution over the dipole. As I mentioned before, we can get over a linear dipole few current distribution. What is common to all those current distributions that we see here is actually that in all of them there are the current is imposed to be equal to 0 at the edges of the dipole. However, along the dipole axis they can vary. And this is something that we can see here, and it depends, this type of current distribution depends on the length of the dipole and the frequency. If we actually substitute those current distribution into the equation, or we take actually the Fourier transform of all those current distribution as explained before, we get actually a closed form expression for the electric field. This closed form, if we plot this closed form expression for the electric field, we get what is called the radiation pattern. The radiation pattern is actually a plot of the amplitude of the field as a function of the angular dependence in space. And here we can actually see the radiation pattern for various current distribution described here. We note here if, for instance, this is the z-axis and this is the y-axis, and the radial extent is actually proportional to the amplitude of the field. It's interesting to note, first of all, that in the zenith, theta equal to 0, and the south pole, theta equal to pi, we get 0 field, and the maximum is obtained for theta equal to pi over 2, as we can note here. We define for the radiation pattern, the angular sketch of the electric field, we define beam width, at which is actually the angular extent for which the power drops to half, or minus 3 dBs. In the case of the elementary dipole, the beam width is equal to 90 degrees. And in the case of a lambda over 2 dipole, the beam width is equal to 70 degrees. Now let's go to another important parameter or characteristics of antennas, which is the directivity. The directivity is actually a parameter which actually tries to quantify the electromagnetic power density in the maximum direction relative to the total radiated power uniformly distributed in space. which is the denominator in this case. The higher the directivity is, we actually get a more concentration of the field in a certain angular range. In the case of the elementary dipole, the directivity is equal to 1.76 dBi, which is obtained actually by taking 10 log to the base of 10 of this expression, and I denotes actual relative to isotropic radiation. For a lambda over 2 dipole, the directivity is equal to 2.14 dBi. The larger the extent of the dipole, we obtain a higher directivity, and this is something that is a parameter for quantifying antennas and getting a better performance. Another important parameter, characteristic of any antenna, and especially the dipole antenna, is actually the complex impedance, Z, which is the impedance that the signal generator feels when the antenna is connected to it. Actually, we can understand the complex impedance by realizing actually that when we connect an antenna to a signal generator, since the radiated energy is lost, therefore the signal generator feels that it's lost to some complex impedance. And this complex impedance is, we denote it by Z. The impedance can be computed numerically using differential and integral methods, which is quite complicated, but we have this kind of tools today, or through a variational expression if we assume the current distribution on the dipole. The expression for the complex impedance Z, which is equal to the real part of the impedance plus the imaginary part of the impedance, XA, is equal to this integral, in which G is actually a kernel with the derivative of e to the minus jkr over r, and multiplied by the current distribution. What is unique in a variational expression like this one is the fact that if we make a small change in I, actually we get a negligible change in the complex impedance. And this is the beauty of this expression, that we don't need to know exactly what is the current distribution. We can also have an estimate of the current distribution, and even though we get a very good approximation of the complex impedance. So, if we assume, for instance, a sinusoidal current distribution on the dipole, like expressed here, we can obtain an analytical expression to this integral by substituting this current distribution into the integral and performing the integral. And this is actually the analytical form of the complex impedance.